Power electronics, power electronics device, UJT and FET. Introduction thyristor का are four layer device which can be switched on या off auto यानी कि जो thyristor और four layer device which can be switched on या off electronically, यानी कि thyristor फोर लेयर क्या है, डिवाइस है जो विच कैन बी स्विच्ड ऑन, जो कि स्विच ऑन ऑफ होता है। इलेक्ट्रॉनिक क्या करता है, स्विच ऑन या ऑफ का काम करता है। इलेक्ट्रॉनिक टू कंट्रोल रिलेटिवली लार्ज अमाउंट ऑफ current for motor and other electrical equipment. The silicon control rectifier ACR and the triac an example of thyristor. Almost all electronics control used in modern industry consist of electronic circuit with thyristor. Construction of ACR. The cross-section view of a typical ACR. The symbol are shown. Pictures 1. Basically, the ACR consists of four-layer plate of P and N type semiconductor material. Silicon is used as the intrinsic semiconductor to which the proper impurity are added. The given pictures ACR, this is the anode and this is the gate and this is junction 1, junction 2 and junction 3, and this is the anode and this is cathode and this is this is the gate and this is the cathodes. This is the symbols represents and this is construction represent. Working of ACR. The ACR is a four-layer device with three terminals, namely the anode, cathodes and the gate. When the anode is made positive with respect to the cathode, junction J2 is reverse based and only the leakage current will flow through the device. The ACR is then said to be in the forward blocking state of state. When the anode to cathode voltage is increased, the reverse base junction J2 will break down due to the large voltage gradient across the deflection layer. This is the avalanche breakdown. Since the other junction J1 and J3 are forward base, there will be free carriage movements across all the three junctions, resulting in a large anode to cathode forward current IF. The voltage drop VF across the device will be the ohmic drop in the four layer and the device is then said to be in the conduction state on state. In the on state, the current is limited by external impedance. If the anode to cathode's voltage is now reduced, since the original deflection layer and the reverse base junction J2 no longer exist due to the free movement of the carriers, the device will continue to stay on. When the forward current falls below the level of the holding current IH, the depletion region will begin to develop around J2 due to the reduced number of carriage and the device will go to the blocking state. Similar, when the SCR is switched on, the resulting forward current has to be more than latching current IL. This is necessary for maintaining required amount of carrier flow across the junction. Otherwise, the device will return to the blocking state as soon as anode to cathode voltage is reduced. The holding current is usually lower than but very close to the latching current. Its magnitude is the order of a few milliampere. When the cathode is made positive with respect to the anode, junction J1 and J3 are reverse based and a small reverse leakage current will flow through the ACR. This is the reverse blocking state of the device. When the ACR is reverse based, the device will have in the same manner as two diodes connected in series with the reverse voltage applied across them. The inner two region of the ACR will lightly doped as compared to the outer layer. Hence, the thickness of J2 depletion layer during the forward base condition will greater than total thickness of the two depletion layer J1 and J3 when the device is reverse based. Therefore, the forward break over voltage VBO will be generally higher than the reverse break over voltage BR. The ACR has two stable and reverse operation state. The change over from offset to on state called turn on is achieved by increasing the forward voltage beyond VBO. Their reverse transmit turn off is made by reducing the forward current below IH. A more convenient and useful method of turning on device employ the gate drive. Characteristics of ACR. Characteristics of ACR. ACR voltage current characteristics picture 2 shown. The voltage current characteristics of an ACR whose gate is not connected or open. When the anode cathode circuit is reverse based is very small current in microampere called reverse blocking current flow through the ACR when the reverse break over when the reverse break over voltage reaches a value equivalent to peak inverse voltage. The ACR conducts due to reverse avalanche breakdown and the current increase sharply into ampere. In most of the case, the ACR gate damage in the mode the behavior of the ACR at reverse base mode is shown by BI characteristics of pictures 2. When the ACR is forward base, there is a small forward leakage current as in pictures 2 called a forward blocking current which remain small until the forward breakdown voltage VBO is reached. This is the forward avalanche region. The launching current on state forward blocking and this is the reverse break over voltage BR, holding current and avalanche leakage current, reverse blocking and this is the reverse avalanche breakdown. At that point current increase suddenly to higher conduction level at the point anode to cathode resistance of the ACR because very small and ACR acts like a closed switch. The voltage across the ACR dropped to about 1.2 volt. Hence, we can say that the forward base mode when the applied voltage is less BFO, the ACR behaves as open switch and when the applied voltage exceeds BFO, the ACR behaves has closed switch. The current through ACR is limited by the external load resistance. Holding and latching current. The holding current is that I value necessary in the anode circuit to keep the ACR in conduction while it is on. The latching current is plus 1 value needed to switch the ACR anode circuit on from the off condition. This I is typically about 3 times more than holding current. When the ACR is switched into condition, the gate voltage must be on log must be on long enough for the anode current to reach the value of latching. The triggering of ACR can be switched into condition either by increasing the forward voltage beyond VBO or by applying a positive gate signal when the device is forward based. Of these two methods, the latter called the gate control method gate control method is used as it is more efficient and easy to implement for power control. Gate current control: injection gate current into the ACR lower the breakover voltage as shown picture 3. Here IGO is for zero gate current. This situation is the same as that shown in picture 2, but the other example in picture 3 are for increasing gate current. Note that as a current is increased, the breakover voltage reduces. This is the on stage. First gate, second gate, यानी G1, G2, G3 and G0 current 0, G1 gate current, G2 gate current, G3 gate current. And the effect of gate current in flowing or lowering the breakover voltage of an ACR. When there enough gate current, the breakover voltage becomes lower than operating voltage, yeah, the forward blocking voltage of the ACR. That is how to ACR is used the injection of gate current lower the breakover voltage to a value below that of the applied voltage, thereby turning the ACR on. Note that the on state is the same from for all different value of the gate current figure 3. The gate current triggers the ACR on, but when the ACR conducts, the amount of forward current is determined by the anode circuit impedance. Application: the following are the major application of ACR. Major application are the following The following are the major application of the ACR. First, power control. Second, voltage protection. Third, timer relay. Fourth, short start circuit. फिफ्थ में है लॉजिक एंड डिजिटल सर्किट. सिक्स, प्लस सर्किट रेफरेंस, पल्स सर्किट रेफरेंस. सेवेंथ, फेज कंट्रोल इन एसिंग पावर कंट्रोल. एट, फुल वेव कंट्रोल सर्किट. नाइन्थ, स्पीड कंट्रोल टू मोटर. एंड टेंथ, regulated DC power supplies. And 11th, DC motor control. Testing of ACR. Testing of ACR by multimeter. ACR can be tested in the multimeter in the following sequence. Set the multimeter to a low range. Adjust to 0 and infinity with adjustment knob. Connect the ACR as known picture 4. The meter will not indicate by any reading even the test plot are interchanged. Because of the junction, the multimeter shown infinity resistance connected the ACR as picture 4. When the gate is touched momentarily with the anode plots, the meter reads low resistance between 30 and 40 ohms. When the gate is removed, the meter still continues to read the same value of 30 and 40 ohms. Given pictures, anode connected to positive of ohm meter. This is positive and this is negative connected to ohm meter, and this is the gate momentarily connected. This is the gate momently connected. And this is the ohmmeter reading dropped to load resistance. This means that the ACR is in good working condition. If the meter does not show any reading, the ACR is faulty when the gate is given a small forward base. The gate switching the ACR and the internal resistance of the junction is low, so the current flow easily from the cathode to anode. Once the ACR is conducted even if the gate forward base is removed. The ACR anode to cathode current will flow through the meter and the multimeter will continue to read a load resistance 30 to 40 ohm. Diac and triac. Like UJTs, diac is a semiconductor device used extensively as a trigger device for triacs and thyristor gate circuit. In its most elementary form, diac is a three-layer device as in pictures 5 without gate terminal. Given pictures 5, this is the anode terminals and this is the anode terminals. This is the anode, this is anode, and this is silicon's pellet, N type, P type, N type, anodes. The base construction of diac, the common symbol for used for diac. As can be seen from pictures 5, diac is a three-layer two-terminal semiconductor device capable of conducting current in both directions. Diac resembles an NPN or PNP bipolar transistor with no base connection. Unlike bipolar transistor, the diac possesses uniform construction. This means N-type and P-type doping essentially the same at the both junction. As in picture 5, diac may be constructed as either in NPN or PNP structure. Picture 6 show the experimental setup for testing the diac. The isolation transformer is used to isolate the circuit from the supply means. The variable transformer is used to apply the variable voltage to diac uniform under the test. The characteristics curve of typical diac is shown picture 6b. 6 is the isolation transformer. This is isolation transformer given 240 volt 50 Hz. This is the variable AC transformer and this is diac voltage and this is 2 kilo ohm resistance. Pictures B, this is anode and this is anode 2. This is ampere plus, this is ampere minus. And break over voltage typically 20 to 40 voltage. Break over voltage 20 to 40 voltage. This is the break over current typically 50 to 200 microampere and this is the rated reverse current typically 180 milliampere at 1.0 volt. This is third quadrant. This is the third quadrant characteristics of diac minus A, break over voltage typically 20 to 40 voltage and this is break over current typically 15 to 200 micro ampere. This is first quadrant and this is rated forward current IF typically 180 milliampere ampere turn 1.0 voltage. As shown in the experimental setup at picture 6a, when a small voltage of either polarity is applied across a diode. The current flow is very small, as can be seen from its characteristics in the first and the third quadrants. If the applied voltage is steadily increased, the current will remain at a low value until the applied voltage reaches a value known as the breakover voltage of the diode, as in picture 6b. Once this point in reaches, the diode current increase rapidly and the diode voltage falls to a low value. At this point, the diode exhibits negative resistance characteristics, current conduction increase while the voltage across the device decrease. The diode will continue to conduct current as long as the current is greater than the holding current of the device. A diode acts in a similar manner to zero-Zener diode that are connected in reverse parallel, and therefore it is able to rectify AC voltage during both half cycle. The symbol used for diode is pictures 5b. Application of diode can be used to trigger triac ACR at specified voltage levels. Diode. Diodes are similar to diodes connected back to back and break down either direction once the applied voltage reaches the breakdown voltage of the diode. While testing a diode using a ohmmeter, it should showing high resistance, infinity resistance when checked in either direction. The quick test only confirm that the diode is not shorted. However, the quick test is worth carrying out before using the diode in a circuit. Triac. Triac is a three-terminal gate semiconductor device from controlling AC in either direction. The term triac stands for triode AC semiconductor. Triac is very similar to that of two ACR connected in reverse parallel. A triac is able to connect to large current in both directions, being triggered on in one direction, the other by a gate pulse of the appropriate polarity. UJT and its application of triggering circuit. UJT are employed in a wide variety of circuits involving electronic switching and voltage other current sensing application. This include first, UJT applicable for triggering triggers for thyristor as isolators, as pulse and sawtooth generators, timing circuits, and regulated power supplies, bistable circuit, and so on. Let us analyze the waveform generated across the capacitor and R1 with respect to relaxation oscillator of free running oscillator as picture 7. Pictures 7 is this is the resistance electronics resistance RB2 and VVV, and this is capacitor resistance RB1 and voltage VB1. Charging and discharging VP1 and 2 volts is the charging, and in this condition this is discharging, and 0 voltage VE and 6 voltage and B1 in this condition. UJT relaxation oscillator. The negative resistance portion of the UJT characteristics is used in the circuit shown picture 7 to develop a relaxation oscillator. The waveform developed across the capacitor is shown in picture 7 as V, whereas the waveform produced across the resistor RB1 is shown as a pulse VB1. The frequency of isolation, and this is frequency is 1 by Re into C, where Re is the value of variable resistor in ohms and C is the value of the capacitor in farad. By varying the value of Re, the frequency of oscillator can be varied. Although such an oscillator using a DC supply voltage uh, could be used to trigger ACR, there would be trouble in synchronizing the pulse with the cycle of alternating current. Pictures 8 shown a stable triggering circuit for ACR in which the firing angles can be varied from 0 to 180 degree. Given a pictures 8, this is RD 39 kilo ohm loads and this is 110 voltage AC 50 Hz. 2N1597 and UJT, and this is 10 ohm RE 10 kilo ohms, R2 100 ohms and capacitor 0.1 microfarad farad, and this is RB1 39 ohm. UJT relaxation oscillator used for triggering SCR, and this is the SCR and this is the UJT. The low output impedance of the UJT 39 ohm is ideal for driving the SCR, which has relatively low input impedance from gate to cathode. Resistor RD is used as a dropping resistor to restrict the peak voltage across the UJT to within a specification. By varying the variable resistance Re, the oscillator frequency can be varied, thereby the frequency of trigger pulses which are used to trigger the SCR. Time used for delay in switching the SCR could be measured through a stopwatch from the time of switching on. Basic construction of triac, its symbol and a typical triac is shown in pictures 9a, 9b and 9c. As can be noticed in pictures 9, the electrodes of triac are labeled as main terminal MT1, main terminal MT2, and this is the gate. The terminals are so labeled because the device operated in both directions and hence the terms anode and cathode does not apply. This is symbol of triac, main terminals to MT2 and beyond contact and heat sink. This is silicon pellet and gate and main terminals. Main terminal MT1. This is TRIAC triac, and this is the triac, 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 and this is the triac, this is the triac and this is triac. MT2, MT1 gate. Triac triggering can be triggered can be triggered turned on by applying the gate current, applying a voltage exceeding the avalanche breakdown voltage VBO, allowing the MT1 minus MT2 applied voltage to increase at a rate in excess of maximum dV by dt figure. Methods 2 and 3 above are not employed in normal triac operation, but they may be considered as limiting factors in circuit design. Hence, in all further discussion, it is restricted to triggering the triac by the gate. Since triac is bidirectional device, it can trigger into conduction by negative or positive gate signal. The triac's potential are considered with respect the main terminal 1 MT1 that gives the following possible operating situation modes. The mt2 positive with respect to mt1 get single positive first quadrant plus mt2 positive with respect to mt1 get singular negative first quadrant. mt2 negative with respect to mt1 get signal positive plus third quadrant plus mt2 negative with respect to mt1 get singular negative third quadrant negative. Unfortunately, track is not equal sensitive in all the above said modes. It is least sensitive in third quadrant mode mt2 negative with respect to mt1 and triggered by a positive gate signal. So this mode is very rarely used in practice. When a track is on, the current flowing between mt1 and mt2 is known as principal current. The track will remain on as long as the current flowing through it is larger than the holding current, as in the statics characteristics of a track in given pictures 10. This is given forward current track यानी कि फर्स्ट क्वाड्रेंट. दिस इज फॉरवर्ड करेंट ट्रायक यानी कि प्लस mt1 पॉजिटिव माइनस mt1 नेगेटिव गेट इज पॉजिटिव and plus mt2 positive get negative and mt1 negative. This is forward current. And second quadrant, reverse voltage latching current and holding current. In this first quadrant, the current gate current 4 ampere and gate current 0 milliampere. And third quadrant, this is gate current 0 milliampere and gate current 4 milliampere. Third quadrant, this is the reverse current, the mt2 plus gate plus mt1 plus and mt2 minus gate minus mt1 plus. Fourth quadrant यानी v80 forward voltage, holding current, latching current. From the triac statics characteristics, when mt2 is positive with respect to mt1, the picture 6 triac operates in the first quadrant of its static characteristics. If it is not triggered, the small forward current increase slowly with increase in voltage until the breakdown voltage BBO is reached, and then the current increase rapidly. The device can be and usually is turned on at a smaller forward current by injecting a suitable gate current, and the characteristics shown the effect of increasing the gate current from 0 to 4 milliampere. The gate current must be maintained until the main current altest equal to the latching current. When the terminal mt1 is positive with respect to m2, the track operates in the third quadrant and the current flow in the opposite direction. Full wave control using a track. Given a picture 11 shows a track used for controlling the current flowing in AC circuit. Pictures 11b shown the waveform with different setting of port BR1. The simplest track control circuit. This is simplest track control circuit. Load voltage, load, this is resistance, variable resistance voltage, capacitor, gate resistance mt1 and mt2. Supply condition, this is the voltage 0 positive and low setting of low setting of voltage resistance R1. This is the load voltage and this is the load current and this is the on and this is the off and this is the off, this is the on. And mid setting of VR1, this is the positive case, positive case, positive case, positive minus maximum positive, positive case. The maximum setting VR1 Maximum setting VR1 track control waveforms. In the track, the turns forward and reverse do not rise since it is bidirectional. Quick testing track. A quick testing can be carried out on track using an ohmmeter. If the reading taken are comparable to the one shown in the table below, the track can be considered as satisfactory and can be used in circuit. Meter polarities resistance MT2, the MT1 is greater than 1 mega ohm, यानी 1 mega ohm. MT2 MT1 MT2 is greater than 1 mega ohm. MT2 is gate resistance greater than 1 mega ohm. Gate MT2 is greater than 1 mega ohm and MT1 may gate resistance greater than 300 ohm and gate MT1 is greater than 300 ohm. Field effect transistor FET. The main difference between a bipolar transistor and a field effect transistor is that bipolar transistor is a current control device. In simple terms, this means that the main current in a bipolar transistor, yani collector current, is controlled by the base current. Field effect transistor is voltage control device. This means that the voltage at the gate, similar to base of a bipolar transistor, controls the main current. In addition to the above, in a bipolar transistor NPN या PNP, the main current always flow through a N-doped and P-doped semiconductor material, where in a field effect transistor, the main current flow neither yani either only through the N-doped semiconductor या only through the P-doped semiconductor as in pictures 12. This is the drain, this is the drain, and this is deflection layer and the electron flow deflection layer, and this is the gate, and this is the gate voltage source and n channels, and this is the source S, and this is the voltage DS. If the main current flow is only through n-doped material, then the such a FET referred as n-channel of n-type FET. The current through n-doped material in the n-type FET is only by electron. If the main current flow is only through the p-doped material, then such a FET referred as a p-channel या p-type FET. The current through p-doped material in the p-type FET is only by holes. Unlike bipolar transistor, in which the main current is both by electron and holes, in contrast in FET depending on the type P या N type, the main current is either by electron, by holes and neighbor both. For this reason, FETs are also known as bipolar transistor या unipolar device. There are a wide variety of FETs. In this lesson, one of the fundamental types called a junction FET yani field effect transistor JEFT is discussed. Junction field effect transistor JEFT, it is three-terminal device and look similar to bipolar transistor. The standard circuit symbol of N-channel and P-channel type FET are shown in picture 30. This is a designations FET N-channel type. gate DS designation, and P channel type D gate and designation. The internal diagram of N-channel FET is shown in pictures 14. This is N-channel FET. This is the drain current, and this is the voltage drain source. This is the electron flow deflection layer. This is deflection layer, and this is the gate and gate voltage source, and this is the N channel source. B drain. This is the drain current. This is the drain current, and deflection layer flow deflection electron flow deflection layer, voltage drain source, deflection layer, gate and voltage gate source, and this is the P channel. This is source. FET notation listed below the external and worth memorizing. Source terminal. It is the terminal through which majority carrier enter the bar N या P bar depending upon type of FET. Drain terminal. It is the terminal through which majority carriers come out of the bar. Gate terminal. These are two internally connected heavily doped region which from two PN junction. Channel. It is the space between the two gates through which majority carries pass from source to drain when FET is working of FET. Similar to bipolar transistor, the working point of adjustment and stabilizing are also required for FET. Basing of JEFT gate are always reverse based. Therefore, the gate current is respectively and practically zero. The source terminal is always connected to that end of the supply which provide the necessary charge carriage. For instance, in N-channel JEFT, source terminal S is connected to the negative of the DC power supply, and the positive of the DC power supply is connected to the drain terminal of JEFT. Where areas in a P-channel JEFT source are connected to the positive end of the power supply and the drain is connected to the negative end of the power supply from the for the drain to get the hose from to the P channel where the hose are the charge carries. Let us consider N channel JEFT. The drain is made positive with respect to source by voltage DS as shown in the picture 15. When the gate to source voltage VGS is 0, there is no control voltage and maximum electron current flow from source S through the channel to the drain D. The electron current from source the drain is referred to as drain current ID. When gate is reverse based with a negative voltage VGS negative as shown picture 15, the static field established at the gate causes deflection region to occurs in the channel as shown in picture 15. This deflection region decreases the width of the channel causing the drain current to decrease. If voltage gate source is made more negative, the channel width decrease. Further, resulting the further decrease in drain current when the negative gate voltage is sufficiently high. The two deflection layer meet and block the terminal. Block the channel. Sorry. Given these pictures, this is drain current, this is electron flow, N channels, gate, and this is VDS. VDS, this is positive, this is negative. This is voltage drain source, and this is the sources, and pictures B, this is drain current, and this deflection layer, electron flow, deflection layer, n channel, and this is the gate source, voltage gate source, and VDS, voltage drain source. Pictures see, this is a drain current and VDS deflection layer, and this is the voltage between gate and channel corresponded to VPS, and this is the gate, and this is voltage between gate and channel is 0 volt. Cutting off the flow of drain current as pictures 15c. This voltage at which this effect occurs is referred to as the pinch of voltage Vp. Thus, by varying the reverse base voltage between gate and source VGS, the drain current can be varied between the maximum current with VGS 0 and the zero current with VGS pinch of voltage. So JEFT can be referred as a voltage control device. P-channel JEFT operates in the same way as explained above, except that bias voltage reverse and the majority carrier of channel are holes. Important specification of typical JEFT, यानी कि पोलरिटी ऑफ द डिवाइस एन टाइप या पी टाइप BF245B NZ और NJ BF मैक्सिमम ड्रेन सोर्स वोल्टेज VDS 30 वोल्ट BFW and maximum gate source voltage VGS 30 volt and BFW 30 volt. And the maximum current, drain current ID maximum forward gate 25 milliampere and BFW 20 milliampere. Current IG gate current, pitch of voltage ID, drain current 0, the VP the 10 milliampere and BFW 10 milliampere. Maximum power dissipation Pmax 30 milliwatt and 300 milliwatt 300 milliwatt. Package type T092 or BFW 10 T072. Pin diagram referred 6605. Data in manual FIG W141E, FIG W158B. The term NJ in the specification indicates that it is N-type junction FET. As discussed earlier, FETs also need a proper biasing arrangement for it to work. Like transistor, FET can also be connected in different configuration. Picture 16 gives a summary and comparison of basic FET configuration. Advantage of FET: since they are voltage control amplifier, this makes their input impedance very high. And two advantage: they have a low noise output. This makes them useful as preamplifier where the noise must be very low because of high gain in the flowing stage. They have better linearity. Given a picture 16. This is the common source configuration. This is common source configuration, and this is common drain configuration, and this is common gate configuration. This is common gate configuration. Fourth number, they have low inter-electrode capacity, typical application of JEFT. One every important characteristics of JEFT is its very high input impedance of the order of 10 to power 9 ohms. These characteristics of JEFT has made it very proper at the input stage of a majority of electronic circuit. As discrete component, FETs are mainly used. DC voltage amplifier, AC voltage amplifier, input stage amplifier in HF and large F range, constant current source, and this is the integrated circuit of both analog and specifically in the digital technology. FET AC voltage amplifier. In the circuit at picture 70, the amplification is determined by the design. It can be varied with a certain limit of the drain resistance and the source resistance are made. Variable potentiometer can be connected in series for this purpose. And this is the circuit diagram of the calculated AC voltage amplifier. AC voltage amplifier.